So what we're going to be taking a look at in this video, or really probably a series of videos, is how we're going to be finding the volume of a three-dimensional object that's going to be created from a two-dimensional uh, graph or shape that's going to be revolved around some line somewhere on a graph, whether it's a x or y axis or some other type of line that you may see. Okay, there are two specific methods that we're going to be looking at in this section, the disk and the washer method. Now the disk, you can kind of think of that like as a just like a quarter, a coin, something like that. It's, where we spin something around and it's gonna, if we sliced it into like if we were, at a deli at HEB or wherever your grocery store is, where they were slicing, something that's essentially what we're doing is we're going to take, some salami or something and pepperoni and slice it up into little thin discs or coin-looking shapes. And the washer method is going to, if you're not familiar with what a washer is, it's kind of a circular shape that has a circle kind of cut out of it, and this is what's left over. And so that's going to be, like where we might have a, think back to what you did in geometry, where you might have had a cylinder that you had to find the volume of, but it wasn't a solid cylinder. It had, a hole that ran all the way through it. And so you would have to find the volume of the big cylinder and subtract the volume of the smaller cylinder. And that's kind of what we're going to be doing for the washer method. Okay, and all we're going to do is we're going to take, some kind of, shape, and the most basic shape would be to take a line. So, we would see something like, where we have an x-axis and a y-axis, and let's pick a color here. And so let's just have a line here that goes between the x and the y-axis. Well, if we were to take that line and revolve it around the y-axis, clockwise or counterclockwise, it doesn't really matter, you would kind of get a reflection of the line here, and it would kind of come around like this, and it would essentially make kind of a cone shape, and where it would, as it revolved around, it would make that kind of a cone-looking shape. And that's essentially what we're going to be doing. Now, the shapes aren't always going to be cones, but that's probably the simplest shape that we would wind up looking at. So here we happen to have that exact same analogy, where we're looking at this one, where we're given the boundaries. R is going to be the region that's bounded between some lines. And in this case, we have the x-axis, the y-axis, and a standard form function of x plus 3y is equal to 6. And we're going to rotate that around the y-axis 360 degrees. So we're going to take it and we're going to spin it around the y-axis like that, and we're going to wind up with a cone-looking shape like what we see on the right. Now, ideally, what we're going to be looking at is to see, well, what is the volume of the cone going to be? Now, this isn't something, because this is a basic cone, this isn't something we specifically need calculus for. If you recall your geometry formulas, volume of a cone is 1/3 pi r squared times the height. So we can find this particular volume really easily by saying 1/3 pi times the radius, which in this case is 6, times the height of 2, and I forgot to square that. And if we were to do that, we would get 36 times 2 and divide that by 3, and that would give us a volume of 24 pi cubic units, whatever they happen to be. Well, what we're going to do is we're going to show how we would take that same process, but instead of doing it with a basic geometry shape, which we can't always use, we're going to be finding the volume with some kind of integration, where we're going to take all of those shapes, whatever the three-dimensional shape happens to be, and we're going to slice it up into a bunch of infinitely small, uh, disks, and take the overall sum of those things. And that's why we're going to be looking at this with accumulation for our integration processes. And what you're seeing here is essentially that idea. So we have the same graph that we're going to be slicing up into smaller and smaller and smaller slices. And so we have this change in the vertical where we have dy, and we want to make that as small as possible. And so we make it infinitely small, and that's really why we want to use an integration process here. But we're going to slice it up into a whole bunch of little discs or coin looking shape that we have there, and we're going to just take the sum of all of those infinitely thin uh, disks and add them up. Where in this case we're looking at a disk where we're saying that the volume of the disk is going to be pi times the radius squared. We have pi times the radius squared. And so essentially this is a small, or this is going to be a cylinder shape. So the volume of the cylinder is pi times the radius squared times the height, where in this case, the change in y is the height and x is the radius. And that's how we get the equation that we have in our little boxed rectangle there. So we've already kind of taken a look at how we would look at the volume. We're still taking a look at the exact same volume or cone that we saw earlier in the presentation, where it had kind of a graph that went like this, where this was 6 and this was 2, and then we spun it around the y-axis. And we've already established that the volume of that cone was going to be 24 pi, and I didn't write that very well, 24 pi cubic units. 24 pi. Well, now let's see how we would take the same approach with integrals, because this is going to be something that you have to use integrals for whenever you're going to have kind of a curvy or a nonlinear segment. Like think of anything that has to do with a parabola or logarithmic functions or exponential functions, anything that's not going to be a straight line. It's going to be more difficult to figure out what the overall volume is going to be without using an integration technique. So let's see how we would do this with integration. So write the volume of the cone as an integral on the interval from 0 to 2, and then find the volume of the cone. Now this here, because they're showing you that the interval is from 0 to 2, that was on our y-axis. So in that case, that means that we're going to be, our cross sections that we saw are going to be perpendicular to the y-axis. And so that means we need to take the function that we had, which the standard form function, I'm not sure why it's not written here. It should be on the same page, those of you that are following along with the notes here. We had our standard form function of x plus 3y 3y is equal to 6. So because we're looking at something where it is going to be perpendicular to the y-axis, we want to solve the function in terms of x. We want to get x by itself. So I'm going to take the 3y and I'm going to move it to the other side, and that would give me x is equal to 6 minus 3y. So this is essentially, this bit right here is essentially the radius of the cone or the cylinder shape that would be made when we take those thin disc slices. Okay, and I just realized I just completely misspelled radius. Radius. There we go. So delta y is going to be the change in the height. That's going to be the height of the cylinder, or in this case, our vertical movement, and that's how we're going to start by finding the volume. So we understand, based on what we saw just a second ago, that the volume, and let me go ahead and switch to a different color here, that the volume of the cone, or I'm sorry, of the cylinder, the disks that we're going to be taking, is going to be pi times whatever the radius is. In this case, we're doing it in terms of x squared times dy. Well, now we're going to incorporate that as an integral. Okay, so I'm going to say the volume of this, and I'm going to pull pi out as a constant, and the integral, the interval of the integral is going to be from 0 to 2 on the y-axis. So we have the x squared here, and we're going to say dy. When we substitute the x squared in, we're going to, or when we substitute our expression for x, we're going to get something that says the volume is going to be equal to pi times the integral of 0 to 2 of 6 minus 3y squared dy. And so now you can see everything in the integrand is going to be worked with respect to y. Now the easiest way to take the integrand here is really, because you've been distributing binomials like this for a long time now, I'm going to go ahead and just distribute the binomial, and I'm going to get my integral from 0 to 2, and when I expand that and distribute everything, writing it in standard form, I'm going to get 9y squared minus 36y plus 36, all with respect to y, times dy. And at this point, we can actually do the integration of each piece of the polynomial that we have. So we're going to keep pi here as our constant, and we're going to take the antiderivative of each piece of the polynomial. So the antiderivative of the 9y squared will wind up being 3y cubed, and then we will get a minus 18y squared plus the 36y, and we're going to be evaluating it from 0 to 2. And again, we already understand that the volume should work out to be 24 pi, because the volume of a cone is very easy to do with the geometry formula. So let's make sure our arithmetic works out. So I'm going to just kind of bring it up here into this white space where I have a little bit more space to write instead of continuing to go down. So I'm going to say volume is going to be equal to pi times, and let's go ahead and start substituting in our numbers, and we'll say 3 times 2 cubed minus 18 times 2 squared, and I didn't go down far enough. Let me erase these here. Plus 36 times 2, and when I substitute the 0, when I substitute, with our fundamental theorem of calculus, substituting 0 for y, all of those things are going to simplify to be 0. So if you want to, you can just say minus 0 to show that after you substitute the y, the lower bound, everything's going to just simplify to be 0 anyway. So again, we'll just go ahead and continue with our discrete operations here. So I'm going to get pi. So 3 times 8 will give me a 24 here. Negative 18 times 4 is going to give me a negative 72. And 36 times 2 will give me a positive 72. And so you can see that the 72s are going to cancel, giving me pi times 24, or 24 pi. And let's see. Let's go ahead and take a look. I know we're getting a little long on time here already, but let's go ahead and try and take a look at the last bit here. Actually, no, I'm gonna go ahead and just pause the video for now, and because we're already about 14 minutes, I'm gonna go ahead and stop this video, and we'll pick it up in the rest of the disk examples for volume. We'll kind of finish that up in a separate video or two. But thanks for watching and take care.